You're fine. You're fine.
Yeah, I'm Yakubu. You said you find it hard to actually pronounce my name. And I'm from Ibrahim Babangida University back in Nigeria. Yeah, I'll be talking about the geometry for a two-part atom interferometer model. Actually, this work has been motivated by the recent search in detecting light-dark matter, as you know, using the new generation atom interferometer, which are normally configured to be sensitive to both tensor and scalar deformations of space-time. Of course, we know generally they are potentially capable for dictating gravitational wave and scalar field, as well as testing a wide range of fundamental physics questions, including gravitational decoherence. More importantly, they are robust. As such, they can be sensitive to deformations in space-time. However, with all these potentials, with all their capability, one of the major problems we have is that many fundamental physics applications still require significant improvement to surpass the sensitivity achieved by the previous method. So it is important finding a way around it on how to improve the sensitivity and setting upper limit on the gravitational wave detection. This can offer an unprecedented potential for new discovery. So for all these reasons, we decide to extend the theoretical framework for improving the sensitivity of the atom interferometer by deriving a broad class of equations which obey specific time symmetry for a two-part atom interferometer. And in doing so, we construct a specific part geometry for the interfering arm, as well as influence functional phase, and deriving the decoherence factor, all in the light of the geometric interpretation for the atom interferometer. So in doing this, we consider equation number 5.
Can you go down?
Yes, it's okay. No, it's okay. Don't worry. It's okay. It's okay. Equation number 5 of reference number 2, which actually is a paper we co-authored with my colleague here. We co-authored and currently is under peer review for subsequent publication. This equation represents the interferometer effect of the two-part atom interferometer with a great translational degree of freedom. Now, this equation, like I said, is defined by some certain parameters. One of the parameters there is the kinetic time, which is the unperturbed, this very time here. I think you can see it. I don't know. Are you hearing me?
Yes, yes, I am.
Okay. Yeah, the kinetic time here, which is the unperturbed frequency, that is the frequency of those atoms as they move from the ground state to the excited state. Also, the term here also defines the mass to energy transition, which is the total ionization energy of the atom. And then we have some specific coupling times here, which is the weak coupling that actually can sense gravitational wave. Now, in doing this, we generalized this very equation to accommodate this geometry I'm about to describe here now. So let's move up a little bit. So let's move on to the second part, which is the two-part atom interferometer model. Now, for this model, we consider a two-atom level, which is described by the Hamiltonian density of this. Now, the parameters, this actually follow the parameter that I've just described in the equation 1. Sorry, I did not label my equations, but the first equation is my equation 1, where the system interaction and the environmental interaction represent the interaction Hamiltonian density. So for simplicity, for the sake of simplicity, we assume that a quantum particle, which is initially at rest at t equal to 0, will split into two. That is the R1, R2. I'm going to show you is in the diagram down below, how we get to that point. So they split into two, and hopefully they recombine at t the initiality equal to the totality, that is the nth of the interferometer phase. So the initial quantum state associated with the two parts are given respectively by this equation here, which corresponds to the density matrix. You can move a little bit upward. Now, the perspective for this model is that when laser light interact with atom, they do so by coherently driving the population of the atom from the ground state to the excited state. Now, having absorbed a lot of photon momentum, they begin to move away from the ground state where they are travel along the two trajectories, that is the two symmetric path. Okay, so you can move on. Let's go to the geometry. Now, you see in this geometry, the interferometer we try to describe here is that the atom, after absorbing a photon momentum, we said they move simultaneously from the ground state and travel along different trajectories, which we have described in this part. Although this part may differ a bit, for this model, we actually consider a symmetric path, so that at the end, they can meet continuously from this point here. So this diagram, move a little bit up, a little bit. Yeah. So the starting point of this approach is based on the classical action of light interaction. We assume that the atom is in the initial frame of reference. The laser interaction affects the motion of the atom, which leads to linear displacement of the atom into a spatial separation of the atom into a symmetric part, that is R1 and R2. This method allows us to calculate the exact interferometric phase shift. So therefore, to calculate the interferometric phase shift, which is the geometry, the following describe the symmetric two-part configuration for the classical part. You can go to the other part of the equation now. Yeah, the first one. Yeah, to this side. Yeah. Okay. That's okay. Yeah, for the classical part, for the first R, we have the coordinates which describe the path through which the atom follow, and the second part which the atom also follow. This represents the coordinates along the two parts. Now, we evaluate equation number 1. I'm sorry, once again, I did not tag those equations. So we now evaluate equation 1 using the explicit component of R1, R2 that is described here, that is described around this point here. So for the time sequence labeled by, there is also a little mistake there, labeled by T. So after using some integral calculus, we arrive at this very equation. You can go up a little bit. Now the value of this, the value here, using equation 6, although I did not tag it, represent the geometric factor for the two-part interferometer. This configuration is actually suitable for time controllable gradient in a differential scheme. So the bottom line here is that this elementary diamond geometry, which is described in figure 1, this can maximize the sensitivity of atom interferometer phase shift to a potential gradient, so that the phase behavior accumulated in the presence of the linear potential can be interpreted as the gradient strength over the space-time area, since we believe that the sensitivity is actually proportional to the two parts. Okay. You can move a little bit to the phase shift. Now, normally, for us to be able to determine the sensitivity, we have to actually look at the decoherence factor or decoherence functional. So by incorporating some vector and tensor component with suitable gauge symmetric, this calculated value for decoherence, you can move up a little bit. Yeah, it's okay. Yeah, so this calculated value for this equation is readily generalized. It's readily generalized for magnetic and gravitational environment. And therefore it is valid for an environment in a Gaussian state, including vacuum or thermal state that can be described by quadratic Hamiltonian. So in conclusion, furthermore, it's okay. Furthermore, we see that the complex part of the decoherence, that is the complex part of the decoherence phase, is actually the value that represents a function of that two part, the classical part which defines the path to which the atoms follow. And the associated decoherence function is given by the ray part. So the exponential value of this represents the factor of reduction for the interferometer interference part for the two-part interferometer. So conclusively, we see that we have derived actually a phase shift value, which represents a geometric factor for a two-part atom interferometer model. Its capability to measure time controllable gradient in a differential scheme for the established equation allows us to better engineer an effective interferometer part, which will be sensitive to weak forces, for example, gravitational waves. I'm sorry, there are a lot of equations that were actually supposed to come into this, but I cannot really capture them on this very poster, but hopefully for the publication, of course, it's going to capture everything. Sorry once more to have delayed this, and I want to also thank the organizer for giving me the opportunity to talk here. Thank you so much.